Hello everyone and welcome to today's video lecture, which is titled The Basel Problem and Beyond. And in today's lecture, what I'm going to do is show you how the great mathematician Leonhard Euler solved the famous Basel problem. Namely, here let's make this smaller so we have more room to write. The Basel problem states the following question. What does the infinite series 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus ... This is sometimes referred to as zeta of 2, zeta being, of course, the zeta function. So the question is, what does this infinite series, which equals zeta of 2, what does this infinite series converge to? Well, Euler shocked the mathematical world when he demonstrated that this series, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, that this series equal to zeta of 2 actually converges to pi squared over 6. Well, that's a pretty amazing discovery in and of itself, but Euler didn't stop there, and neither will we. We're going to also show in this video how Euler was able to apply his methods to then calculate zeta of 4, which is 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th, as well as zeta of 6. We'll show how he calculated that. Zeta of 6 is 1 over 1 to the 6th plus 1 over 2 to the 6th plus 1 over 3 to the 6th, and so on. And Euler was actually able to demonstrate the values for zeta of 8, zeta of 10, and so on. But let's just start with the Basel problem. So the Basel problem, again, is summing the infinite series 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on. Now, we know from the integral test that this series does converge. Euler's contemporaries knew that the series converges as well. The problem, however, is that trying to sum this series directly, trying to just add up the terms to get some kind of grip on what this series might converge to, doesn't really help us solve the problem, because this series actually converges very slowly. To see why that is, you can refer to my previous video on the Euler-Maclaurin summation formula, where I show how Euler figured out a very quick way to estimate what this series converges to, because manually summing it up is such a slow process. And I won't prove this argument again here because I do that in my previous video, but the point is that if we were to try to sum up zeta of 2 manually, we would need to add up 1,000 terms just to guarantee accuracy to 2 decimal places. And even then we wouldn't have a very good picture of what this series is actually converging to. So when Euler published his result, that zeta of 2 equals pi squared over 6, he became famous overnight. And I mean, it's just kind of an amazing result, right? Like, why should the sum of the reciprocals of the squares have anything to do with pi? But we'll see that it does. So let's follow Euler's amazing argument to prove that zeta of 2 equals pi squared over 6. Now, to do that, I'm going to ask you to recall the following fact, which is that the Taylor series for the function sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, plus x to the 9th over 9 factorial, minus ... And then we can divide both sides of this equation by x to find the Taylor series for the related function sine of x over x, and that equals 1 minus x squared over 3 factorial, plus x to the 4th over 5 factorial, minus x to the 6th over 7 factorial, plus x to the 8th over 9 factorial, minus ... plus ... So that's the Taylor series expansion for sine of x over x, which was known not only to Euler, but known by all of his mathematical contemporaries. But Euler went a step further and discovered that the function sine of x over x can also be written as an infinite product, which I'll display in a moment. But if you're at all mystified by that idea that sine of x over x can be written as an infinite product, I encourage you to see my previous video on the infinite product expansion for sine x, where I lay out how Euler made that amazing discovery. Anyhow, Euler discovered that sine of x over x can be written as the following infinite product expansion. Sine of x over x equals open parenthesis, 1 minus x squared over pi squared, close parenthesis, times, open parenthesis, 1 minus x squared over 4 pi squared, close parenthesis, times, open parenthesis, 1 minus x squared over 9 pi squared, close parenthesis, times 1 minus x squared over 16 pi squared. And I hope you see the pattern now. Each term in the infinite product expansion is a binomial of the form 1 minus x squared over n squared pi squared, where n is a positive integer. So we have these two different representations for the function sine of x over x. One is an infinite series and the other is an infinite product. The second one is an infinite product. And so the natural question emerges. If these two representations for sine of x over x are equivalent, as we know they must be, then that essentially asserts that if we were to somehow multiply out the infinite product expansion for sine of x over x, if we were to multiply this infinite thing out, we would recover some kind of sum. We would actually recover our Taylor series expansion for sine x over x. Well, multiplying out an infinite product, such as we have for sine of x over x, might seem like a tall order, but all we have to do is just follow the ordinary procedures that we would always follow for multiplying out polynomials. And when we do that, we have to remember that as we expand this expression, each term in each of these binomials can only multiply one other term. So when we do this expansion, we're going to form lots of different products. One such product that we can form clearly right away is the product 1 times 1 times 1 times 1, and so on. In other words, we can make it such that all of these 1's just multiply each other. And if we were to carry out that process infinitely, we would just end up with the constant term 1. And what do you know? That corresponds to the constant term 1 that we see up there in our Taylor series expansion for sine of x over x. Well, how would I get a term with x squared in it? Well, one product that has x squared in it is the product formed by multiplying negative x squared over pi squared times 1, and then times 1 again, times 1 again, times 1 again infinitely. That will give me the term negative x squared over pi squared. But that's not the only way to get an x squared term in this infinite product expansion. I can also let that first 1 in the first binomial multiply the term negative x squared over 4 pi squared, and then let that term multiply 1 and multiply 1 again and multiply 1 again, infinitely so on, just multiplying 1, 1, 1, 1, 1. That will give me the term plus negative x squared over 4 pi squared. I'm also going to have a plus negative x squared over 9 pi squared when I let that term in that binomial there multiply all the other 1's in all the other binomials. Following this same process, I'm going to have a plus negative x squared over 16 pi squared when I expand out this infinite product, and so on. So when we expand this infinite product expression for sine of x over x, we find that our x squared terms are all of this form. So I can factor out that negative x squared there, and I'll find that its coefficient is actually the infinite series 1 over 1 squared times pi squared, plus 1 over 2 squared times pi squared, plus 1 over 3 squared times pi squared, plus 1 over 4 squared times pi squared, and so on, dot, dot, dot. But here's Euler's amazing insight. We know that this infinite product expression for sine of x over x, which we're expanding out, must equal the Taylor series expression for sine of x over x. So we know that negative x squared times, open parenthesis, 1 over 1 squared times pi squared plus 1 over 2 squared times pi squared plus 1 over 3 squared times pi squared, dot, dot, dot. That must equal negative x squared over 3 factorial, because those are the only two terms in both of these expressions that have an x squared in them. So these coefficients of x squared, on the one hand, the infinite series 1 over 1 squared pi squared plus 1 over 2 squared pi squared plus 1 over 3 squared pi squared, etc. And on the other hand, the 1 over 3 factorial, these coefficients of x squared must be equal to each other because they both are multiplying the x squared term in either the Taylor series expansion or the expanded version of the infinite product expression for sine of x over x. So we can set these two things equal to each other and cancel out the minus x squared from both sides of the equation. Now I'm just going to factor out that pi squared from the denominator of all those terms on the left-hand side, and I'm going to rewrite 3 factorial as 6, which is what it equals. And then I'll multiply both sides of this expression by pi squared, and so I get that the expression 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus ... that equals pi squared over 6. But the expression on the left-hand side of that equation is just zeta of 2. So, by this method, we get Euler's solution to the Basel problem, which is that zeta of 2 equals pi squared over 6. Pretty awesome. Now, many presentations of this topic stop there, but Euler actually didn't, and neither will we. We'll go ahead and follow Euler to derive values from these two different but equivalent expressions of sine x over x to derive values for zeta of 4 and zeta of 6. I believe Euler actually got as far as deriving zeta of 12. We're not going to go that far, but I do want to show you the process for how you can get subsequent values of zeta of x on even integers. So we'll do that now. So the first thing we need to look at is how we would determine the coefficient for the term x to the fourth by expanding out the infinite product formula for sine of x over x. And notice, by the way, that there's no way to get an x cubed term or an x to the fifth term. We only get even powers of x, which is reflected in the fact that in the Taylor series for sine x over x, we only see even powers of x as well. In fact, sine of x over x is an even function. It's symmetric about the y-axis. But anyway, to get the term for x to the fourth, well, we know from the Taylor series that its coefficient is 1 over 5 factorial. In the Taylor series, our x to the fourth term is x to the fourth over 5 factorial. So we know that's going to be equal to the coefficient that we'll get from expanding out sine of x over x and collecting all the x to the fourth terms on the right-hand side of this equation. Well, how do we get x to the fourth terms when we expand out the infinite product formula for sine x over x? Well, the first one would be minus x squared over pi squared times minus x squared over 4 pi squared times 1 times 1 times 1 times 1. In other words, followed by an infinite string of 1s. So I'm not going to include that infinite string of 1s there. That's not necessary. I'm just going to write down our first x to the fourth term, which is represented by the product minus x squared over pi squared times minus x squared over 4 pi squared. And I'll just put those together in parentheses. The next x to the fourth term would be the result of multiplying negative x squared over pi squared by negative x squared over 9 pi squared. So to write out all the terms in that product would be negative x squared over pi squared times 1 times negative x squared over 9 pi squared times 1 times 1 times 1 times 1, etc. So I'll just group those together again in parentheses. The next product giving us an x to the fourth term would be the result of multiplying negative x squared over pi squared by negative x squared over 16 pi squared. So to get that, I do negative x squared over pi squared times 1, and then it hits negative x squared over 16 pi squared, and then it's just followed by multiplying a string of 1s. And we can continue producing x to the fourth terms in this way, having the term negative x squared over pi squared multiply only 1s, except one time multiplying a negative x squared term in one of this infinite chain of binomials. So that's what this ... term represents here. It's all of the possible products of negative x squared over pi squared with the other x squared terms in the infinite product expression for sine x over x. But that's by no means the only way to produce x to the fourth terms. We can also do it by starting with negative x squared over 4 pi squared, having it multiply that 1 to the left of it, and having it multiply negative x squared over 9 pi squared to the right of it, and then an infinite string of 1s after that. So I have to include that term also in my collection of x to the fourth terms, the term negative x squared over 4 pi squared times negative x squared over 9 pi squared. Come to think of it, I would also have the term negative x squared over 4 pi squared times negative x squared over 16 pi squared, and negative x squared over 4 pi squared times negative x squared over 25 pi squared, and so on. In fact, if we started with negative x squared over 9 pi squared, I could have that term multiplying negative x squared over 16 pi squared, and so on. So what am I essentially saying here? In order to get all of the possible x to the fourth terms by expanding out the infinite product formula for sine x over x, I have to take all possible pairwise products of negative x squared terms in the infinite product formula. When we do that, we note again that this sum must equal x to the fourth over 5 factorial. So now we can simplify the expression on the right-hand side. I'm going to factor out an x to the fourth over pi to the fourth from all of those products. And then the x to the fourths will cancel, and I'm going to multiply both sides of the equation by pi to the fourth to cancel that out from the denominators on the right-hand side. Well, what does that then give us? We get that pi to the fourth over 5 factorial equals this very interesting sum, the sum of the products 1 over 1 times 1 over 4, plus 1 over 1 times 1 over 9, plus 1 over 1 times 1 over 16, plus dot, 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 and then plus 1 over 4 times 1 over 9, plus 1 over 4 times 1 over 16, plus dot, 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 plus 1 over 9 times 1 over 16, plus 1 over 9 times 1 over 25. We've got the sum of all possible pairwise products of the reciprocals of the squares. Now, for those of you who watched my previous video on the Newton-Girard identities, hopefully for some of you a light bulb is going off in your mind right now, because you might realize, as Euler did, that that sum, the sum of all these pairwise products of the reciprocals of the squares, is actually the elementary symmetric polynomial on two elements, where your elements are 1 over 1, 1 over 4, 1 over 9, 1 over 16, and so on. If you're at all confused by that concept, I highly encourage you to check out my video on the Newton-Girard identities. It's on my YouTube channel. And in that video, we called the elementary symmetric polynomial on two elements E2. The Newton-Girard identities are a set of formulae, first published actually in full by Isaac Newton, that relate different types of symmetric polynomials. One type of symmetric polynomials that I've just brought up, the elementary symmetric polynomial, takes the sum of all possible pairwise products of elements, or triplet products of elements, or quadruplet products of elements, and so on. And the Newton-Girard identities relate these elementary symmetric polynomials to another group of symmetric polynomials called power sums. And those are polynomials of the type x1 to the n plus x2 to the n plus x3 to the n, and so on. So under this interpretation, if our terms under consideration are 1 over 1, 1 over 4, 1 over 9, 1 over 16, and so on, then in fact, zeta of 2, which equals 1 over 1 to the first, plus 1 over 4 to the first, plus 1 over 9 to the first, plus 1 over 16 to the first, and so on, can be considered to be P1, the sum of all elements to the first power. In fact, under this interpretation, zeta of 2 could also be considered to be equal to the first elementary symmetric polynomial E1, the sum of all singleton products, in other words, the sum of all individual terms. That's E1, the elementary symmetric polynomial on one element, and it equals P1. Knowing that, we're now in a position to find zeta of 4. Because zeta of 4 just equals 1 over 1 to the fourth, plus 1 over 2 to the fourth, plus 1 over 3 to the fourth, plus 1 over 4 to the fourth. That's the same thing as 1 over 1 squared squared, plus 1 over 2 squared squared, plus 1 over 3 squared squared, plus 1 over 4 squared squared, and so on. Zeta of 4 is just equal to the power sum of squared terms. It's just equal to P2. So let's collect all of these facts together again. We have that pi to the fourth over 5 factorial equals the sum of all pairwise products of terms like 1 over 1, 1/4, 1/9, 1/16, 1/25, and so on. And that can be represented by the elementary symmetric polynomial on two elements, which I call E2. We also have that zeta of 2, which we found to be equal to pi squared over 6, can be represented by the first power sum polynomial P1, as well as by the elementary symmetric polynomial on one element, E1. Now, why is it so helpful to realize that these expressions are symmetric polynomials? Because we can use the Newton-Girard identities to determine zeta of 4. Because we know that if zeta of 4 equals the power sum P2, from the Newton-Girard identities, we have that P2 equals P1 times E1 minus 2 times E2. Plugging in our values for these symmetric polynomials, we have that zeta of 4 equals pi squared over 6 times pi squared over 6 minus 2 times our value for E2, pi to the 4th over 5 factorial. 5 factorial is 120, so 2 over 120 is 1 over 60. So we then get pi to the 4th over 36 minus pi to the 4th over 60. The common denominator here is 360, so we get this equals pi to the 4th times 10 over 360 minus 6 over 360, and that equals pi to the 4th times 4 over 360, and finally reducing that fraction, we get that zeta of 4 equals pi to the 4th over 90. That's very cool. Now let's go ahead and find zeta of 6 the way Euler did. Well, if we wish to obtain the x to the 6th term from our infinite product formula for sine x over x, we would get a sum of the type negative x to the 6th over pi to the 6th times 1 over 1 times 1 over 4 times 1 over 9 plus negative x to the 6th over pi to the 6th times 1 over 1 times 1 over 4 times 1 over 16 plus negative x to the 6th over pi to the 6th times 1 over 1 times 1 over 4 times 1 over 25 plus plus negative x to the 6th over pi to the 6th times 1 over 4 times 1 over 9 times 1 over 16 plus negative x to the 6th over pi to the 6th times 1 over 4 times 1 over 9 times 1 over 25 plus plus negative x to the 6th over pi to the 6th times 1 over 9 times 1 over 16 times 1 over 25 plus and so on. This sum will equal our x to the 6th term in the Taylor series, which is negative x to the 6th over 7 factorial. So on the left-hand side of this equation, I can factor out from all those terms a negative x to the 6th over pi to the 6th. And then what happens? The negative x to the 6th terms on both sides of the equation will cancel. We'll then multiply both sides of the equation by pi to the 6th. And so I'll end up with this sum on the left-hand side equaling pi to the 6th over 7 factorial. Now, what exactly is this sum on the left-hand side of the equation? Well, it's just the elementary symmetric polynomial on 3 elements. It's the sum of all possible products of my terms 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, 1 over 36, and so on. It's the sum of all possible products of those terms taken 3 at a time. So this is the elementary symmetric polynomial on 3 elements, known as E3. So E3 equals pi to the 6 over 7 factorial. And again, we also have that P1 equals E1, which equals zeta of 2, and that equals pi squared over 6. Recall that we also found that E2 equals pi to the 4th over 5 factorial, or 120. We used those facts to find P2, which equals zeta of 4, and we found that that equals pi to the 4th over 90. Lastly, we observed that the elementary symmetric polynomial on 3 elements, where our elements are the reciprocals of the squares, E3 equals pi to the 6th over 7 factorial, which equals pi to the 6th over 5040. So we're going to use all of those facts and the Newton-Girard identities to find zeta of 6. And in order to do that, we have to realize that zeta of 6, which equals 1 over 1 to the 6th plus 1 over 2 to the 6th plus 1 over 3 to the 6th plus 1 over 4 to the 6th, that zeta of 6 can also be written as 1 over 1 squared cubed plus 1 over 2 squared cubed plus 1 over 3 squared cubed, and so on. And now what does that equal? That just equals 1 over 1 cubed plus 1 over 4 cubed plus 1 over 9 cubed plus dot dot dot. So if these are our elements, 1 over 1, 1 over 4, 1 over 9, etc., then 1 over 1 cubed plus 1 over 4 cubed plus 1 over 9 cubed plus dot dot dot, that's just the power polynomial P3. And now by the Newton-Girard identities, P3 equals P2 times E1 minus P1 times E2 plus 3 times E3. So let's plug in our values. We have then for P3 zeta of 6 equals pi to the 4th over 90 times pi squared over 6 minus pi squared over 6 times pi to the 4th over 120 plus 3 times pi to the 6th over 5040. Okay, so that equals, factoring out the pi to the 6th there, pi to the 6th times 1 over 540 minus 1 over 720 plus 1 over 1680. And when you do the calculations and find a common denominator and simplify that expression, we get that zeta of 6 equals pi to the 6th over 945. Well, I hope it's clear by now that by utilizing these methods, we can successively calculate zeta of 8, zeta of 10, and so on. And so that leads to the natural question, is there a formula for zeta of 2n? And as it happens, yes, there is. But in order to derive that formula, we need to explore the Bernoulli numbers even further. So I'm going to stop there. Thank you so much for watching this video, and if you enjoyed it, please like or subscribe to my channel. Thanks again.